Today we're going to talk about inverse variations. And remember that we can solve inverse functions, and we're going to be able to compare direct and inverse variations. So today we're going to learn what an inverse variation is. How do I recognize an inverse variation from a graph, a table, or an equation? And then how to solve problems involving inverse variations. Okay. So let's just quickly review direct variation is, if you remember, y equals kx. Okay, so if I am looking at a table, we're actually going to find k. So k is y divided by x, and we want to make sure they're all the same. So in the case of this first table, 4 divided by 2 is -2. 2 divided by -1 is -2. 0 during 0 is fine because it has to go through the origin, right? And then -2 divided by 1 is -2. So this is a direct variation. If I take, in the next example, 1½ divided by 5, that's going to give me 3/10. If I do 1 8/10 divided by 6, that's going to give me 3/10. If I do 2.1 divided by 7, 3/10. But if I do 2.1 divided by 8, it's going to give me 0.2625. So this is not a direct variation. And right off the bat, I can see that 24 divided by 2 is 12. 16 divided by 3 is 5 point something. 12 divided by 4 is 3. So this is not a direct variation. So just a quick review of direct variation. Okay. So when we did direct variations, I gave you a bunch of examples. So I want you to take a look at these and jot down some ideas of what you think makes an inverse variation. I'm also going to add under inverse variation this graph as well. Okay. We usually do look at just this because inverse variations tends to be ways to model real world data. So a lot of times in the real world we don't have negative times and that kind of thing. So notice that the inverse variation is this nice little curve and it doesn't touch that x or y axis. Remember that this is a direct variation. It goes through the origin and is straight line. This is a quadratic, which we're just finishing up. And this is an exponential, but you're not going to learn that till Algebra 2 or after, deciding whatever you take. Okay. Inverse variations here, xy equals 9, xy equals 110, and y equals 12 over x. If you would multiply by x, you would still get xy equals 12. Here, if you divided by x, you would get 110 divided by x. And here you would get y equals 9 over x. So you see they're all similar. Again, this is a direct variation. This is linear. And this is a quadratic. Okay? So those are not inverse variations. Okay? If I was going to solve for y, I wouldn't get that 9 over x. Here I've got a constant, so it's going to make it linear. And here it's got that squared, so it's going to make it a quadratic. Okay. So all of these are inverse variations. Take a minute and see if you can figure out what they're going to do. With direct, remember we divided x and y. Here, what we're going to do is we'll multiply. 2 times 50 is 100. 4 times 25 is 100. All of these, when I multiply, are 100. So xy equals 100. Here, 1 times 12 is 12. 2 times 6 is 12. 3 times 4 is 12. 4 times 3 is 12. So here, xy equals 12. In this example, if I multiply, I get -200 all the way down the chart. So the equation for this would be xy equals -200. So notice if I multiply these and get the same thing, it's inverse. Okay. So if I'm going to recognize an inverse from a variation, we're going to say that it doesn't cross the x and y axis or touch. I guess that should be or y. And it's going to have this nice little curve to it. So it's not going to touch that. Okay. An equation, it's going to be of the form y equals k x, and k is our constant of proportionality again, or our constant of variation, or xy equals k. Okay, so again, there's the table. We're just going to multiply that x and y is going to equal the same thing. All right, so inverse variations are of the form y equals kx, I'm sorry, y equals k divided by x, or xy equals k, and k is the constant of variation again. Okay. So let's look at some examples. Let's assume that xy varies inversely as x, and we want to write an inverse variation that relates x and y and then graph it. So x times y equals k. So if we put this in here, we're going to get 2 times negative 5 equals k. So k is going to be negative 10. Now that's great, we found k, but our equation is going to be either y equals negative 10 or y equals negative 10 over x. Those are our equations because we want to be able to substitute things in for x and y. For example, if I go to graph this, it helps if I have a table. Okay, if I put 1 in for x, negative 10 divided by 1 is negative 10. So I have the 0.1, negative 10, which is going to be here. If you look at the graph, it's going by 2's. Okay, if I put 2 in for x, I'm going to get negative 10 divided by 2, which is negative 5. So that's going to be right about here. Okay. If I put 5 in, and notice I'm just picking numbers that are divisible by 10 because it's going to make it a lot easier to graph. So negative 10 divided by 5 is negative 2. So right here. And if I put 10 in, I'm going to get negative 1. So my graph is going to look like this. Okay. Now, if I do the same with the negative numbers, if I put negative 1 in, I'm going to get positive 10. If I put negative 2 in, I'm going to get positive 5. If I put positive 5 in, I'm going to get positive 2. And if I put negative 5 in, if I put negative 10 in, I'm going to get positive 1. So it's going to kind of have this mirror image. Okay, 2 positive 5 would be, oops, 110 is actually going to be here. So 2, negative 2, 5 is going to be right here. And negative 5 and 2 here. Screwing up the scale there and there. There's positive 1. So it's going to look like this. Okay, it's never going to cross our x and y axes. Okay, let's do one more. Okay, so in this case, same directions, xy equals k. So k equals negative 6 times negative 6, where k is positive 36. Our equations are xy equals 36, or y equals 36. Sorry, k over 36. Okay, so I'm going to graph it. I'm going to make it, I was right the first time. Miss Craig's losing it. It's SOL season. What do you expect? 36 over X. All right. So if I make a table to graph, if I have 1, which isn't really feasible because it's not on this graph, and we're going up by 4s. So if I do, let's do, if X is 2, 36 divided by 2 is 18, so that's not really on the graph. If I go divide by 3, I'm going to get 12. If I divide by 4, I'm going to get 9, and 6 will give me 6. So 218 isn't on the graph, but 312 is. And like I said, the scale is 4. So actually this will be 12 here. So 212. And these are approximations. Or I'm sorry, 218. 312. 49. And 66. Right. And if I was to put 9 in, I would get 4. So we're going to go really, really close to the line. And with the real world, and then we're going to have the exact replica over here. Okay, those are the graphs. So in the real world, those numbers aren't so neat. So now let's write an inverse variation that relates x and y and assume that y varies inversely as x and then solve. All right. So we've got x and y. So we know x, y equals k. So 14 times 8 equals k. So k is 112. So our equation, again, is either x, y equals 112 or y equals 112 divided by x. All right, so those are our equations. So when we go to find y when x is 2, we're just going to put in 2. I would use this equation because it's already solved for y. So y equals 112x, or divided by 2 because we're going to sub in 2. So y is going to equal 56. So when x equals 12, y is 56. So there were 3 steps in solving this. Okay, I found k. I wrote a formula basically that would work with any number. So if I knew that x was 10, y would be 11.2, and then I found y. Okay. Here's another example, same directions. Okay, write an inverse variation. So x, y equals k. So k is going to equal negative 48 times negative 4, or 192. Our equations are xy equals 192, or y equals 192x. Okay, so when x is 6, what's y? Y equals 192 divided by 6, and that's going to give me 32. Again, when we write this general formula, what if I knew that x was, I'm just going to go with 10. I could find y. Okay, so 10y equals 192. Y would equal 19.5 by dividing by 2. So remember, we're trying to write that general formula so that we can pick any value of x or y and find the other one. All right, I know you love word problems. These are different than the ones that are on the video, just because I didn't really like the one on the video, so you might want to take a second to write this down. Okay. So the water level in a river varies inversely with air temperature. When the so water varies inversely with air temperature. So let's just say water times air temperature equals K. So there's how we can find K. When the air temperature was 90, the water level was 11 feet. If the air temperature was 110 degrees Fahrenheit, what was the level of the water in the river? So we want to write an equation so that we could solve this. So WT equals K. So we know that when the air temperature was 90, the water was 11. So 90 is the temperature, the water is 11. So K is going to equal 990. Okay, so my equation is either xy equals 990 or it's not even xy, it's WT in this case. All right, so there's our equation. And if the air temperature was 110 degrees Fahrenheit, so for temperature, for T, we're going to put in 110. So W times 110 equals 990. And we know we can solve that by dividing by 110. So W equals 9 degrees Fahrenheit. Okay. And these are real world problems. This one's physics. You might be doing stuff like this in your science class this year. When two people are balanced on a seesaw, the distance from the center of the seesaw are inversely proportional to their weights. So if a 118-pound person sits 1.8 meters from the center of the seesaw, how far should a 125 person sit from this balance? So I know that a lot of you guys have been on seesaws, right? So you know that if you want things balanced, okay, the heavier person always moves in closer, while the lighter person moves out. All right, so let's just give them X. So we've got distance times weight equals K. So in this case, a 118-pound person sits 1.8 meters. So 1.8 meters times 118 is going to give me K to be 212 and 4/10. Okay. So my equation could be XY equals 212 and 4/10. So now, how far should a 125-pound person, and again, I keep going back to X and Y, D and W, so a 125-pound person times the distance equals 212 and 4/10. Remember, the commutative property tells me it doesn't matter what order I multiply in. So if I divide both sides by 125, I'm going to get distance to be approximately 1.699 feet, or if we wanted to round, 1.7 feet. Okay, so a lot of information about inverse variation today. We learned how to recognize them on a graph, a table, or an equation, and then how to solve real-world problems. And my second period finally has come up with my tagline, have a math-tastic day.